typical modern home contains an extensive network of wiring supplying mains power and connections between telephone and internet devices, security systems, audio and television. This wiring acts like a large antenna, which can pick up amateur transmissions and cause interference to other devices and services. The extent to which EM fields can cause interference to other devices is called electromagnetic compatibility, or EMC. The European EMC directive sets standards for resistance to EM fields for electrical and electronic devices. This is called immunity. Not all imported equipment meets this standard. We'll see in the next few slides how we can help to identify and prevent interference from our station, causing problems to other nearby equipment or properties. The transmitted RF field strength is at its maximum close to the antenna. Other nearby cables and wires can also act like antennas and couple to your antenna, causing RF current to flow in them. If the antenna is close to the house or someone else's house, it may couple into the internal wiring. This end-fed antenna has the vertical radiating section close to the house, which increases the risk of stray coupling into house wiring and other devices. A better solution would be to reverse the antenna and feed it at the point furthest from the house. You should be aware of and avoid placing your antenna close to nearby overhead cables, such as telephone wires, which may affect telecommunication equipment connected to them. Your neighbour's property should also be considered when choosing the location for your antenna. Broadcast receiving antennas and any antenna preamplifiers connected to them are susceptible to strong EM fields from your antenna, and this should be avoided. Unbalanced antennas, such as end-fed wires and ground-mounted verticals, use the ground as a return path to the transmitter for antenna current. If an RF ground is not provided, or if the RF ground is poor, the antenna can couple into the 240-volt mains safety earth and the house wiring. In this example of an end-fed long wire, the antenna current flows up the center conductor of the feeder along the antenna. The EM field from the antenna then couples into the ground by a process called capacitive coupling. This causes the return current to flow through the ground back to the RF ground earth for the transmitter, in this case a ground spike. The current flows back to the ground spike to the transmitter via the screen of the coaxial feeder. If the RF ground connection to the antenna is poor, the antenna will find an alternative ground to couple into. This is usually the house wiring and the mains safety earth. Poor RF ground can be improved by adding ground radial wires or a counterpoise to the antenna to take the place of the poor ground connection. If a poor RF ground connection causes stray RF current to return to the radio via the ground connection, it can easily couple into the house wiring through the power supply and other equipment connected to it. This device is an RF choke, designed to allow the low-frequency AC mains voltage and current to pass unhindered, but to block any RF current that might be present on the mains leads from your radio equipment. This particular design from GM3 SEK is shown feeding a multi-way extension cable that powers all the radio equipment in the radio room. This large example of a clip-on ferrite core is used in this design. Passing the cable through or around the core causes resistance to the rapid frequency changes of the RF current and helps to block it. A smaller example is shown here, which can be clipped onto the cable with no need to cut the cable. Several chokes of this type may be needed in series on the cable to achieve the required choking impedance. This is another example of a ferrite ring called a toroid, where the mains cable has been wound around the core 6 times to multiply the choking impedance. Clip-on ferrite RF chokes can be used to good effect wherever radio equipment is connected to computer equipment, or where interference to any equipment is thought to be caused by RF current. This diagram shows the incoming mains electricity supply to a typical domestic property. Note that the mains safety earth, shown as the green conductors on the diagram, is connected to any conductive objects within the house by a process called earth bonding. It's essential that you do not use the main safety earth or any metal pipework in your home to provide your RF ground. RF current may appear on the mains wiring and can be transferred to nearby properties as well. This installation is of a type called TNCS, or Terra, meaning earth, neutral, combined and separated, TNCS. The safety earth for such a property is derived and connected to the neutral cable as it enters your house. With TNCS systems in particular, you must consult a qualified electrician before installing an RF ground spike to ground your radio equipment. Failure to do so can cause high voltage to appear on your ground earth if a fault occurs on the incoming supply cable to your house. TNCS systems are now very common and are found in houses either built or rewired in the last 50 years. A solution to this might be to use an artificial earth for your radio equipment, such as a counterpoise wire. Small household devices, such as baby alarms, can be affected by something called direct pickup into the circuit and internal wiring if there's a strong RF field nearby. This can be more of a problem at VHF and UHF, since the very short wavelength means that even short wiring can act as an effective antenna to your signals. Another common route of entry into equipment for RF current from your antenna are the long speaker wires connected to hi-fi systems in the home. Modulated signals, especially AM and SSB, can easily couple into such systems and be heard through the audio amplification stages. Devices in the home that may already be radio receivers or have circuits that are very similar to those in radio receivers can easily demodulate amateur transmissions if there are strong RF fields present. Digital receivers are not immune to RF interference from amateur transmissions. This often manifests itself as pixelation or freezing of digital TV pictures or dropout to digital radio signals. The picture on the right shows a typical digital TV signal that's being affected by RF interference from a nearby amateur transmitter. Whatever the problem, if you are contacted by a neighbour about possible case of interference, you must deal with it cooperatively and in a non-confrontational way. Loss of goodwill to a neighbour may result in complaints to Ofcom and investigative action being taken. Log keeping, while not a requirement of the licence, is always good practice. If an accurate log is kept, it's easy to see if the interference is present at times when you may not be transmitting, and therefore could be from another source. The RSGB offer help on their website to track down and deal with interference. Ofcom can also be contacted if the interference problem cannot be solved. The RSGB also offer a dedicated advice service via an email address that you will find on their website. Modern vehicles are highly complex, often with multiple computers connected by databus systems. RF current entering any of these systems can cause malfunctions to critical safety systems. You should seek advice from the vehicle manufacturer, your vehicle insurer, and the user handbooks for the equipment to be installed before attempting any installation. If you're unsure about how to go about fitting radio equipment to your vehicle, you might consider asking a professional auto electrician to do the work for you. Thorough testing must be done with the vehicle stationary to ensure that no critical systems are being affected by RF interference. Audio breakthrough into other devices is most noticeable with amplitude modulated signals, with SSB being the worst offender in this respect. SSB has far more power applied to the modulation envelope than AM, although either can cause problems under similar circumstances. The problem is that any equipment that has any form of receiving stage or audio amplifying stage capable of reproducing audio sound can easily demodulate an amplitude modulated carrier wave if there is sufficient RF coupling into it, such as may occur with a nearby amateur transmitter. The carrier envelope will be demodulated and amplified by the affected device. This can appear as speech-like interference in the loudspeaker in a manner that people find particularly annoying. FM modulation is less susceptible to simple demodulation, as it is the frequency changes, not the amplitude, that carry the modulation. the amplitude remains constant and is less likely to be demodulated by simple means. A CW signal that's been shaped to avoid hard switching edges in the carrier envelope, such as can be seen in this oscilloscope display, are also less likely to cause this kind of interference, although key clicks and thumps may still be heard. Electromagnetic fields, or EMF, can cause harm to the human body if you are exposed to RF fields above a certain strength for longer than a certain time, or if the peak power exceeds 100 watts EIRP at any time. You must prevent exposure above these levels to the general public. This is anyone, except yourself as the operator, but it does include family members. You're required to assess the risk of exposure and prevent exposure to any member of the public if you emit RF radiation above a certain field strength at a certain distance from the antenna. For the foundation license, this is deemed necessary if the radiated power from the antenna exceeds 10 watts EIRP or 6 watts ERP averaged over a 6-minute period. The regulations say you must make an assessment of your station for EMF field strength, even if you think that you are below the power level needed for further action. The RSGB provide an online assessment form that makes this process very easy, and we'll look at this in the next slide. The link to the RSGB EMF assessment page is shown here. Power to the antenna is measured at the feed point, after any feed line losses have been taken into account. However, the gain of the antenna must also be taken into account, either as gain compared to an isotropic antenna, which is EIRP, or compared to a dipole, which is ERP. Remember, directional antennas with higher gain will radiate higher power in the direction of maximum radiation. This is the calculator tool provided by the RSGB on their website for making the assessments of your EMF compliance. It's simple and quick and allows you to save the completed assessment as a PDF file, which you can then download and keep in your records. Use the configuration drop-down menu to add your name, address and station details. We then enter the frequency band we intend to assess. EMF assessments vary with the wavelength of the radiated signal. We select the mode of operation, in this case SSB. We then enter the maximum transmit power we intend to use and assess how long in each 6-minute period we expect to be transmitting. A good estimate would be around 50% of the time. Note that the calculator tool has populated these boxes with the average and peak transmit power over that period. We can then start to assess power loss in the feeder. You can select a range of common feeder cable types or type in the loss per 100 meters from the manufacturer's datasheet if known. Here, the length of the feeder cable needs to be entered to calculate the total loss in dB. Note that the calculator tool has now worked out the power at the antenna feed point based on feeder losses. Finally, we add details of the antenna to assess its gain. Here I've shown a half-wave dipole, which is a common antenna for the 20-meter band. We must enter the polarization of the antenna and the height above the ground at its lowest point. The calculator has now taken all this information into account and provided the EMF assessment for maximum radiated power over the 6-minute period. Note that since the EIRP is below 10 watts, the assessment has shown your station is compliant on the 20-meter band, with a maximum transmit power of 25 watts on SSB. For higher transmit powers at intermediate and full license levels, it's often the case that the assessment requires further action to be taken. If so, the assessment produces minimum compliance and separation distances that you must observe when transmitting. This is an example taken from my own station for the 80-meter band using SSB at a maximum power of 200 watts. Although you are not examined on this, you should be aware of what happens if further action is needed to protect the general public during the assessment. You must ensure that the compliance distance is maintained from any part of the radiating antenna and the closest part of any person, usually their head, that is likely to come within the EM field of the antenna when transmitting. Since my antenna is 10 metres off the ground, and there is no part of it closer than 2.4 metres to any member of the public, that would be my neighbours in their gardens or any family member in my garden, then I am deemed to be compliant. We really appreciate you taking the time to watch this video. Don't forget to check the video description where you'll find additional information about the video you've just watched, along with links to products used and to the Haddai's website. If you enjoyed this presentation, please feel free to hit that like button. Maybe you'd also consider subscribing and clicking the notification bell so we can let you know the next time we release another video. Thanks again for watching.